Alright, so today we're going to be talking about this thing called L'Hopital's rule. And essentially, recall that when we were initially doing limits, there were some limits that we could not evaluate because they took on special forms, but L'Hopital's rule will now give us a powerful tool to be able to do that. And so L'Hopital's rule says that if a function at some limit takes on an indeterminate form, then limit as x tends to a of that original function, which we can write as two functions, f of x divided by g of x. So I'm writing that original function just as the quotient of two functions. Its limit is just the same thing as the limit as x tends towards a of the f prime of x divided by g prime of x. So essentially what it's saying is that if I have some, so I haven't described what an indeterminate form is, but if this original limit over here takes on an indeterminate form, we can find the derivative of the numerator and divide it by the derivative of the denominator, evaluate the limit of this new function, and that is the limit of the original function. And so there's a lot of different indeterminate forms, and the plan is to go over each of them and do examples with each of them. And so the first indeterminate form I'm going to cover is this one. It is 0 over 0. Essentially, when we're trying to apply this limit, we get 0 over 0, and that does not help us find out what the limit is. So let's do a concrete example of it. Remember that when we were trying to find the limit as x tends to 0 of sine x over x, I told you guys just to take it to be 1 for now, and later on we would actually know how to find this, and now it's the time to find this. So if we were to just plug in 0, we would get 0 over 0, since sine of 0 is 0, and then x is just 0. And that's not a valid form to be able to find the limit. Nor can we use any tricks to be able to re-express this function to be able to find the limit. So our only choice is to use L'Hopital's rule, which says that this limit is the same thing as the limit as x tends to 0 of the derivative of sine x, which is just cosine x, divided by the derivative of x, which is 1. And plugging in 0 now will give us 1, and this matches what I told you the limit would be, and it also matches where we would see the function tending towards when we graphed sine x over x. And the only reason we could have applied L'Hopital's rule is because when we tried to evaluate this function at 0, we got an indeterminate form. A function must take on this indeterminate form for us to apply L'Hopital's rule. So let's solidify this through more practice. Let's evaluate the limit at x equals 0 of the square root of 1 plus x minus 1 divided by x. If we were to plug in 0, our numerator would be 0, our denominator would also be 0. So we can apply L'Hopital's rule. The derivative of the numerator is simply 1 plus square root of 2 times 1 plus x divided by the derivative of 1, which is just 1. And so the limit as x tends to 0 of this new function is simply equal to 1 plus square root of 2, or 2 times the square root of 1, which is 1/2. Let's do a new problem. Limit as x tends to 0 of 1 minus cosine of x divided by x plus x squared. If I were to plug in 0, I would get 1 minus 1, which is 0. And then 0 plus 0 is simply 0. So this is an indeterminate form. We can use L'Hopital's. And so this derivative of the numerator is simply sine x. Denominator's derivative is 1 plus 2x. And then limit of this as x tends to 0 is simply 0 divided by 1. And so the answer is 0. Note that in this in part B. Before, like, we could have still, like, if I didn't teach you L'Hopital's, the trick before would be to multiply this numerator and denominator by the conjugate, and it would give us a better form to be able to solve this limit with our older tools. But now that we have L'Hopital's rule, we have much more powerful tools to be able to evaluate limits, and this just goes to show that L'Hopital's is not the only way to solve a limit, but it can help when there's no other ways, such as part A, where we didn't have any other form or ability to solve limits. Let's do one more. Let's do a few more. So part D, limit as x tends to 0 of the square root of 1 plus x minus 1 minus x over 2 divided by x squared. If I were to plug in 0, this would be 1, minus 1, 0, minus 0 minus 0 is 0, so that would be 0 on the numerator, denominator 0, so correct indeterminate form. This is the same thing as limit as x tends to 0 of the derivative of the numerator, which is 1 over 2 square root of 1 plus x minus 1 half divided by x squared. Now, if I were to treat this as the numerator and this as the denominator, I would notice that the numerator is simply 1 half minus 1 half, which is 0, and the denominator is 0. So we're still at an indeterminate form, but that's okay. We can continually recursively apply L'Hopital's rule, and we can find the derivative of the numerator, which is simply equal to minus 1 over 4 times x plus 1 to the power of minus 3 over 2. And then our denominator would be 2x. Now, or actually over here our denominator was 2x, and then over here our denominator is 2. Now, if you plug in 0, our numerator becomes minus 1 over 4 times 1, and then denominator is simply 2, and then this is minus 1 over 8. So sometimes we have to apply L'Hopital's multiple times, but that's okay. That's completely fine, and that's completely legal. Now, L'Hopital's rule also applies to one-sided derivatives. And so let's look at some problems related to that. Let's find the limit as x tends to 0 from the positive side of sine x divided by x squared. Plugging in 0, we would get 0 divided by 0. So that's indeterminate. So that's the same thing as the limit as x tends to 0 from the positive side of cosine x divided by 2x. Cosine x is, from the positive side, is going to be, well, it's 1 both ways. And then 0 from the positive side is 0. And now that will give us positive infinity. Now, I guess another example is limit as x tends to 0 from the negative side of the same function. And we know that this is the same thing as limit as x tends to 0 from the negative side of cosine x over 2x. We know that cosine of 0 is 1, and then now the denominator would be 0 from the negative side. Hence, we're tending towards negative infinity. So L'Hopital's rule still helps us with one-sided derivatives. It can also help us see that if a function is tending towards infinity or not. So we covered the indeterminate form of 0 over 0. Now, the next three indeterminate forms are infinity divided by infinity, infinity multiplied by 0, and infinity minus infinity. So these are also indeterminate. And when we see these, we can also apply L'Hopital's rule like we saw before. So let's work with functions that take on these forms. So let's find the limit as x tends to pi over 2 of secant x divided by 1 plus tan x. Secant is 1 over cosine, and so secant of pi over 2, we know is simply going to be well, secant of pi over 2 is going to tend towards cosine, like 1 over cosine pi over 2, which will go towards infinity. So that will take on infinity, and then tangent of pi over 2 will also similarly go towards infinity. So we get one of those indeterminate forms. So let's find the derivative. So it's the same thing as finding the limit as x tends to pi over 2 of secant x tangent x divided by secant squared x. This simplifies to tangent x over secant x, which we can simplify further. Times cosine x. And so we're just finding the limit as x tends to pi over 2 of sine x, which is simply 1. Now, let's work with another problem. Limit as x tends to infinity of the natural log of x divided by 2 times square root of x. And we know just by analyzing like the end behavior of these functions, we get infinity over infinity. So I'll find the derivative of the numerator, which is 1 over x. Derivative of the denominator is simply 2 divided by 2, the derivative of the denominator is 2 times 1/2 times x to the power of negative 3 over 2. So that becomes 1 divided by x to the negative 1/2, which is equal to x to the 1/2. Or, sorry, what? This becomes 1 divided by, or 1 over x divided by x to the negative 3 over 2. Or 1 over x times x to the negative 3 over 2, which is simply equal to 1 over x to the negative 1, x to the 1. Alright, this is too many mistakes. Yeah, so I get 1 over x. I get 1 over x divided by 2 times 1/2 times x to the negative 1/2. And that is equal to 1 over x divided by x to the negative 1/2. And that is simply equal to 1 over 1 over x to the 3 over 2, and then that will tend towards 0 in the limit. Alright, let's continue on. Limit as x tends to infinity of x sine 1 over x. Now, as x goes towards infinity, this is clearly going towards infinity. And then sine 1 over x as x tends to infinity is like getting closer to sine 0. So this is infinity times 0. So how do we deal with this? With this indeterminate form? So one thing we can do is we want to convert this into a way that we get f of x over g of x. And one way to do that is we can let the variable 1 over x is equal to w. And that will help us rewrite this limit as w tends towards 0 from the positive side, since as x tends towards infinity, w will tend towards 0. So rewriting this, we get limit as w tends towards 0 of 1 over w times sine w. And notice how this is still indeterminate of 0 over 0. And so this is completely valid change of variables. And we've already seen this before, but once we take the derivative with respect to w, we get cosine w over 1, and the limit as w tends to 0 from the positive side of that is simply 1, and that solves our limit. Alternatively, we could have just treated x as sine 1. Alternatively, I think we could have just written this in a different form and solved for the limit, but either one works. Now let's do limit as x tends towards 1 of 1 divided by natural log of x minus 1 over x minus 1. Log of x or log of 1 is 0, so this is positive infinity. And then this is also the same thing where we have 1 or 0. So we have this infinity minus infinity form. And the idea is like, we saw that when we had the infinity minus infinity or 0, or the 0 times infinity form, we want to try to get it to a 0 divided by 0 form like we did over here. And with an infinity by infinity form, we also want to try to get it towards a 0 over 0 form as well. And one way we can do that is we can combine the fractions, and when we combine the fractions, we get x minus 1 minus natural log of x divided by x minus 1 times ln x. And now, over here in this numerator, what happens is we get 0 in the numerator because 1 minus 1 is 0, and then log of 1 is also 0, so this will be 0, and then the denominator similarly will be 0. And if we can now use the derivative, we find the derivative of the numerator, which is simply 1 minus 1 over x. Derivative of the denominator, we have to use product rule, which is 1 over x times x minus 1 plus log of x times 1. If we were to plug in 0 now, we would still get an indeterminate form. Well, let me first rewrite these fractions. So this becomes x minus 1 divided by x divided by x minus 1 plus x ln x divided by x, and then that's the same thing as x minus 1 divided by x minus 1 plus x ln x. And so this, in this format, if we were to find the limit as x tends to 1, we would still get 0 on the numerator, and the denominator would be 0 as well. And so we have to refine the derivative of both sides, so that's the same thing as limit as x tends to 1 of 1 divided by 1 plus 1 over x times x plus 1 times ln x. And now this becomes 1 as well, so we have this is equal to simply 1 over 2. So that was the indeterminate form of infinity minus infinity. Let's now cover the last bit of indeterminate forms. So the last few indeterminate forms are in the form of 1 over infinity, or 1 to the power of infinity, 0 to the power of 0, and infinity to the power of 0. So these are also indeterminate. And to find out the limits of these indeterminate forms, we use this strategy. So the limit of, as x tends to a, of the logarithm of f of x will be some number L. And that's like the essential idea of the fact that we're going to take the log of these functions, and that will help isolate out the infinity or like the power. And once we get that, we can simply take e to the L, and that will be the limit of as x tends to a of f of x. So this rule of limits helps us find the original limit, and hopefully concrete examples makes this more clear. So let's find the limit as x tends to infinity of 1 plus 1 over x to the power of x. We see that as x tends to infinity, this will become 0. So this is in the form of 1 to the power of infinity, which we have said is indeterminate. If I were to take the log of this function to help isolate out, or to help like take this power into like a coefficient rather than becoming a power, then the natural log of 1 plus 1 over x to the x is simply equal to x times the natural log of 1 plus 1 over x. And the limit as x tends to infinity of that is simply going to be in the form of infinity times 0, since the natural log of 1 is 0, which is also indeterminate, but we can rewrite this. Well, we have to apply L'Hopital's rule, and the way we apply L'Hopital's rule is first we rewrite this as the natural log of 1 plus 1 over x divided by 1 over x. So notice how this and this original form is the same thing, but I'm writing this in a way that helps me apply L'Hopital's rule, since now I get a clear f of x and a clear g of x. So finding the derivative of the numerator and the denominator, I get, I'm finding the derivative of this, so the numerator's derivative is 1 over 1 plus 1 over x, and then using chain rule, I multiply by negative 1 over x squared, and then my denominator is simply negative 1 over x squared, so all of that cancels out, and so this is the same thing as the limit as x tends to infinity of 1 plus 1 over x, and that's the same as 1. But since this is the limit of so since this logarithmic function over here is the limit of the log of the original function, then I know that the original function's limit is simply e to the power of 1, because I have to now, like, e to the log of f of x is simply equal to, well, so the limit as x tends to infinity of e to the power of log f of x is simply equal to the limit. And so I take e to the power of 1, and that's my limit. Let's continue working with these indeterminate forms. So I want to find the limit as x tends to 0 from the positive side of x to the power of x. Again, the best way, the indeterminate form here is 0 to the power of 0. And the best way to work with it is using this logarithmic limit rule. So the natural log of x to the power of x is simply x times ln x. So now I'm trying to find the limit as x tends to 0 from the positive side of x ln x. And so this takes the form of 0 times negative infinity, which is just the same as like infinity times 0. So I have to use L'Hopital's. And so to use L'Hopital's, let me rewrite this as limit as x tends to 0 of ln x divided by 1 over x. And that's the same as limit as x tends to 0 from the positive side of 1 over x divided by 1 over x squared, the negative of that. I rewrite this as negative x squared divided by x, and I get negative x. And so I'm finding the limit as x tends to 0 from the positive side of negative x, and hence I get simply that is equal to 0. Now I have to take e to the power of 0, which is equal to 1, and so that's my limit. And I have to do the e because of the fact that I took the log of the original, and that's how I calculate the derivatives later on. Let's do one last problem. So part B. Find the limit as x tends to infinity of x to the power of 1 over x. So now I get something in the form of infinity to the power of 1 divided by infinity. So infinity to the power of 0. Again, this is indeterminate. Every time we're working with exponents, it's probably better to use the log rule of limits. So the natural log of x times to the power of 1 over x is simply 1 over x times ln x. Now my indeterminate form is simply infinity over infinity. We already know that that's an indeterminate form. And so that's the same as the limit as x tends to infinity of 1 over x divided by 1. And that's just 0. And now we take the power, so now we just simply calculate limit as x tends to infinity of e to the ln f of x. And we already know that ln f of x tends towards 0, so this is just e to the 0, which is 1. So we worked with all of these. So there are no more indeterminate forms. And to summarize, the indeterminate forms are as such. So these are indeterminate forms. We started with 0 over 0. Then we had infinity over infinity. We had infinity times 0, infinity minus infinity, 1 to the power of infinity, 0 to the power 0, infinity to the power 0. And we saw that like with these power ones, it's often easier to find the limit of the log of the function and then once again take e to the power of the function. With these two ones, infinity times 0 and infinity minus infinity, it was often easier to try to use techniques to get it into one of these forms. And also when you, similarly, it can be said that with these exponent ones, we often got it into these forms and then use L'Hopital's. And then finally, if we have something in 0 over 0 or infinity over infinity, we can plainly keep using L'Hopital's until we can evaluate the limit. So L'Hopital's rule in general gave us a very powerful tool to evaluate limits, and now with the power of L'Hopital's rule, in addition to all the different manipulations of finding limits before, we should be able to evaluate basically every limit.